Hi, welcome back. In this video, we're going to talk about finding specific attributes of a polynomial. And we'll do so in the following videos as well. Now, this will be a bit of a review, so it'll be very similar to factoring polynomials, except that we're going to be focusing on the x and y intercepts. So more like the solutions as opposed to the factors. So I want to go over two examples and just kind of clarify the differences between the two, while also reviewing the rational root theorem. So let's go about it. So we want to find the x and y intercepts. Let's start with the x intercepts. So we're going to use the rational root theorem, right, to find the x and y just the x intercepts, where this value is p and this value here in the front is a q. And we're going to continue to do the factors here, right? Factors of p, it's going to be 1 times 9, 3 times 3. Right, 1, 3, and 9 are the factors of 9, and then also the negative versions of these. -1, and -3, -9. Those are all factors of -9. At the same time, we're going to have q. The factors of 1 are just going to be 1 and -1. Now, as you start to do this more often, the more you start to realize that you can figure out which ones repeat faster and stuff. So here, when we simplify all of these, the unique values are going to come down to 1, -1, 3, -3, 9, and -9. You're welcome to do the fraction, right? 1 divided by 1, 1 divided by -1. 3 divided by 1, 3 divided by -1. 9 divided by 1, 9 divided by -1. And then repeat for all the numerators divided by 1 or -1, and these are the unique values. Now these values are all x-intercepts. These are all possible solutions, or x-intercepts, right? This is known as the rational root theorem. So it produces roots where it crosses the x-axis. That's what this theorem produces. It tells you where it crosses the x-axis. So these are all possible solutions on the graph already. Yeah? And we're going to use the rational root theorem to identify it. We have 1, -6, 8, 6, and -9. And we're going to try every one of these solutions to see which one gives me a 0 as a remainder. Let's start with 1. 1 times 1 is 1. When I add these, I get -5. 1 times -5 is -5. When I add them, I get 3. 1 times 3 is 3. When I add those, I get 9. 1 times 9 is 9. When I add those, I get 0. So that means that x does equal 1. I have one x-intercept already, and I'm looking for 4 possibly. Yeah? Which means I have 3 left over, or a cubic. Okay? Now we're going to continue this process, and since these numbers are all factors of 1 and 9, right, we're going to continue to use these possible solutions. This is me abbreviating possible solutions. Yeah? So let's try this again with the new cubic. 1, -5, 3, and 9. And I'm going to do this with, and I can try it all over again, right? I can start with 1, -1, 3, -3. I can continue this process. Let's start with 1. 1 times 1 is 1. When I add these, I get -4. 1 times -4 is -4. When I add these, I get -1. -1 times 1 is -1. That does not give me a 0 solution. So then I continue this process with -1. -1 times 1 is -1. As I add these, I get -6. Negative times a negative is a positive. When I add them, I get 9. -1 times 9 is -9, and when I add those, I get 0. I found my second solution. So far, I have 2 solutions, -1 and 1. Right? 1 and -1 are my solutions, which means I'm left with a quadratic. Now, at this point, I can convert this to a quadratic, or I can continue the rational root theorem to solve the rest. Right? I can do this and factor 1x squared minus 6x plus 9 if I wanted. When I factor this, it'll give me x times x and negative 3 times negative 3. Now, the key thing to understand here is that we're leaving the rational root theorem to a different method. These are all rationals, these are all solutions, but this is going to create factors. So it's important to distinguish, right? The fact that these are already solutions, these are in factored form. I would still have to set each of those equal to 0 and solve for x, which are both going to turn into x equals 3, right? The x equals 3 being repeated. That's the key distinction here, is that if we're going to leave the rational root theorem, we're going to now use a factor methodology to find the solutions. But the factors are not solutions. We're one step away from solving. So you have to set each factor equal to 0. Now, if you don't want to switch methods, you can continue here and use the rational root theorem, 1, negative 6, and 9. And you can continue by finding the factors of more values that we're dealing with. We can plug in with 3. 3 times 1 is 3. When I add them, I get negative 3. 3 times negative 3 is negative 9. Notice how this also works. Yeah. The only thing here to understand, though, is that while this gives me the solutions, I don't know whether or not something else gets repeated here. And here, I know that the x minus 3 is repeated twice. And here, we're going to have to kind of experiment to identify if we have 3 unique x-intercepts or 4 x-intercepts with one of them being repeated, right? So the x-intercepts are x equals 1, negative 1, and because this is repeated twice, x equals 3. But I want to emphasize how the rational root theorem creates solutions while factoring creates factors. And we then separate each factor and solve for x to find the solutions. Yeah? Now, these are all the unique x-intercepts. We now then want to find the y-intercept. And when you look at this polynomial, the y-intercept is where it crosses the y-axis. So whether the y value is positive or the y value is negative, what do we know about that x value? The x value is always at 0. So if we plug in 0, let's switch pens here. If I plug in 0 for x here, I'm going to get 0 to the 4th power. That goes to 0. 0 to the 3rd power. That also gives me 0. 0 squared. That gives me 0. 6 times 0. That gives me 0. Right? 0 minus 0 plus 0 plus 0 minus 9. The y-intercept is negative 9. And now I can graph a function that gives me these polynomials, right? I can do an example of something that looks like it's got to go through negative 1 as an x-intercept, positive 1, positive 3, and it also has a y-intercept of negative 9. It's going to be somewhere down here at negative 9. And I can do a graph that goes through all of those points while also being a positive x to the 4th, which means it's going to look like this. Yeah. Now, because this value is being repeated, we can go through all these other videos, combine the information, right? It's going to look something like this. It's going to go through at negative 1, it's going to go through at 1, but because 3 was repeated, it's going to bounce at that location. And that was another video for graphing polynomials that you can look back at. Anyway, here's an example of how to find the x and y intercepts, right? The key thing that we wanted to focus on here was the difference between a factor and a solution. All of these are already solutions. And if you're going to switch to factoring as a method, you need to convert the factors two solutions. That's the key distinction that I wanted to focus on for this unit, right, for this portion of the unit. All right, let me know if you have any questions. I hope this has helped, and it's been more of a review of a previous video that we made. If you would like more examples, you're welcome to go back to the factoring polynomials part 1 and part 2, where I do a lot of examples. This is just to clarify the difference between rational root theorem creating solutions as opposed to factors and then solutions. You guys have a great day, and don't forget to subscribe, and as always, I'll calculate.